Greetings, fellow calculus fanatics, oh lovers of epsilons and deltas. Okay, so brief summaries. We worked on tailored polynomials on Wednesday. The idea is actually quite simple. You want a polynomial such that its derivatives at a point match the derivatives of a given function at a point. And when you only do that to the first term, that's our standard linearization about a point. But you can do a non-linearization and have a quadratic term and a cubic term and things like that. So that's the idea of Taylor approximations. Just matches derivatives. When the function can be differentiated infinitely often, like e to the x, its derivative is e to the x, and so its 100th derivative is also e to the x. And when you evaluate that at, say, the origin, you just get 1. And so all of these coefficients become 1, 1, 1, 1, 1. And you get a very simple expression. It's one of the, probably the only Taylor series that people memorize because it's quite straightforward. We mentioned that, the fact that you're doing 1 and x squared allows you to imagine putting something else in there besides a scalar, as long as you interpret 1 as the multiplicative unit in the reals. You could replace that with the identity matrix, which is the multiplicative unit for n by n matrices. And then you put an a in here, and you put an a in there, and you square it, and you cube it. All that makes sense. And in fact, it will turn out to be very important to us when we study linear systems of linear differential equations. And your eigenvalues and eigenvectors will become important to you in a way that we couldn't really do well in Rob 101. So that's going to be cool. In case you're interested, you can read through this to show that there's nothing really special about e to the x, except that it just makes some of the numbers easier. Okay, you could take 3 to the x, and then you could do 3 to a matrix. I've never seen this written down. I'm sure I'm not the first human being on the planet Earth to have ever fantasized about that, but yeah, e to the power a is what we normally do. Okay, so what we're working on today is taking derivatives from a scalar value function that depends on a scalar and extending that to functions of several variables. And we got started on that on Wednesday. We have this funny symbol that's called partial that replaces the d that we have with an ordinary derivative. And it's to indicate that we're doing something a little bit different, but not much different. How different? Well, the partial of f with respect to x1 is the derivative of the function when I vary x1 and hold x2 constant. You see, I'm perturbing only the first variable, x1. I'm perturbing the first variable, and x2 is just fixed. So it's being treated like a constant, and that's exactly the definition of d with the classic d with respect to x1, only one derivative. And similarly, the partial derivative with respect to x2, you perturb the second component, keeping the first one unchanged, and you're getting a rise over run, with the run being induced on the second component and the rise coming from changing the second component. So it's really just differentiation of one variable at a time. Well, looks funky. Once you do a few, it becomes easier. And so we did this one practice problem at the end of class. So we got a function that depends on x1, the product of x1 and x2 and x2 squared. And the idea is when we differentiate with respect to x1, we hold x2 constant. So derivative of x1 with respect to itself is just 1. x2 is a constant, so we have a constant times x1. That derivative is just the constant, and that's why x2 is here. And when x2 is constant, its change with respect to x1 is 0, so that's why the 0 is there. And you would just write that as 1 plus x2, but I just wanted to show all of the terms. And if we do df by dx2, we treat x1 as a constant, so its derivative is 0. We treat x1 as a constant, so the derivative of this is just x1, the constant. And the derivative of x2, well, the usual differentiation rules apply. It's the power rule. The 2 comes down, and we subtract 1, and we end up with 2x2. And because it's differentiation one variable at a time, the usual chain rule, quotient rule, product rule, all of those rules apply. So, get out your paper and pencil as a warm-up. Let's just make sure we have this idea locked down, and I'll give you 2 minutes to compute the partial derivative with respect to x1 of the given function. And if you got that, then we're going to build on it. If you don't have it, we're going to fix it. So folks online, feel free to punch in your answers, and Max can critique them. If you got the first one, the second one's going to follow the same thing. So, how we doing? Got the first one? Okay, that's probably enough. Okay, so what's your thought process? What's the derivative of cosine?
Negative sign.
Negative sign, okay? So it's what this is an application of the chain rule. So we need to differentiate cosine. So we did minus sine. We have to plug in everything that's in the argument. x1, x2 squared. And then we differentiate the argument with respect to x1. Why x1? Because it's a partial with respect to x1. Okay? And so then the derivative of this with respect to x1, x2 is a constant, and so this just becomes x2 squared. And why I said once you got the first one, the second one is pretty much the same because, okay, we got to differentiate with respect to x2. There is an x2 inside the function, so it's once again the chain rule. Derivative of sine, and we leave the argument in there. Then this time we differentiate with respect to x2. And x1 is a constant, so we end up with times, well, there's an x1, I'll write them in the order that you would do them if you were just doing them, but obviously we would write that as 2x1, x2 in any kind of report that we were doing or something. Okay. Does that match what you got, or did I make a mistake? Okay, because I figured you guys probably make fewer mistakes than me. Okay, so that's what partial derivatives are. And then all their applications will be doing mostly on Wednesday, getting going with that. Okay, no questions? Let's do it. Okay, so what would you do if the function is not scalar valued? So this only has one row, okay, taking values in R, and there's only two vectors here, variables here instead of n. So how do you extend this to some function is mapping Rn into Rn? How to do that? Just needs better notation than what we did before. Space. Okay, so let me write x in terms of all of its components so we can see them. Okay, it's a function from Rn, so it's there's n components there. If we're going to evaluate the derivative at a point, it's going to have n components as well. And then the function, it's an M vector, so it has the first component, second component, and an mth component. So how do we manage holding all the components of x constant except for one of them at a time? Well, this is where linear algebra comes in. You may or may not remember the natural basis vectors from Rob 101. E1 has a 1 in the first component. E2 has a 1 in the second component. And finally, En has a 1 in the last component. And these are all n by 1 vectors, so the basis vectors in Rn. Okay. Does that look sort of familiar? Yeah, so they're called the natural basis vectors, the canonical basis vectors, okay, so they're basis vectors. Now, if I were to take the vector x0 that has n components, and I add h times ei to it, where absolute value of h is small, what have I done? So ei is going to have zeros everywhere except on the ith row, correct? That's its definition. So I'm holding everything constant except the ith component of x. That's exactly what we were doing up here. We got x1 plus h. That could be x1, x2, well, for you, plus h times e1. So it would just give a change in the first component. And then similarly, if I were to add e2, it gives a change in the second component. So this is a perturbation. That's what derivatives are about, perturbing the function around it to find local slopes. It's the perturbation in the ith component of our point x0, okay? So it's the easiest way to hold everything constant but one variable. And that's the whole notion of partial derivative. Essence of partial derivatives. Okay, so once I now know how to do a simple perturbation, I can define partial derivative of my function with respect to the ith component at the point x0 to simply be the limit as h goes to 0. I perturb in the ith component, so I get the rise over run with respect to one component changing. I am changing the ith component, and I'm perturbing it just a little bit because I'm taking the limit as h goes to 0. So it's still a rise over run. Here's a second take. You only have to have one of them that makes sense to you, okay? So don't worry about it. So I'm going to define a function that depends only on h. So it's scalar. It's a function of a scalar variable, a single variable, so ordinary derivatives. And this function is simply f of x0 plus h ei. x0, that's just a number. H, that's a value, a variable. Ei, that's just a constant vector. So this only depends upon h. And so the partial derivative with respect to xi at x0 is exactly the same thing as the derivative evaluated at h equals 0. So it's just an ordinary derivative taken one variable at a time. So that's the thing I want to have. This would be the limit, h goes to 0, gi of h minus g at 0 over h. Rise over run. Now, there's lots of rises and there's one run. Why are there lots of rises? Because in the first component, we've got the rise over run of f, the first component of f, and the second part of that vector is the slope rise over run of the second component of the function, and in the last is the rise over run. So that's happening, whoops, where'd you go? That's happening here. It's the rise over run is the entire function, f1 through fn, only perturbing xi. Am I beating a dead horse? You guys got this? Is one variable at a time? Or should we? I'm beating a dead horse? You got it? Okay, sorry. Don't mean to be embarrassing you myself by making it seem like I'm treating you like children, okay? But this is, the key thing is this is a function of a single variable. Okay, so that's how we define partial derivatives in general. We hold everything constant except the ith variable, and we do ordinary derivatives with respect to that. Okay, we're going to do all of this in vocarium in just a little bit. Do you remember when we introduced derivatives, we did the rise over run as one way of looking at it. Then there was a second way that we looked at derivatives. Anybody remember what that might be? Now ringing a bell. I must not have attached enough pizzazz. Excuse me?
Like a linear approximation.
Whoa, okay. There's at least one neuron that got triggered by that, and associative memory brought it back. Yeah, so linearization. Okay, so once again, we have our function, depends on several variables, and it has several components. We have a fixed point, and we'd like to approximate the function by something linear, near x0. So we're trying to write the function as f of x is approximately, I'm going to go ahead and write in the first term so there would be a linear approximation, so this is n by 1 f is m by 1 so A has to be m by n. But what is it? What goes in there? So when we did it for scalars, I went ahead and wrote a B here, and then I put an A here, and then we plugged in x equals x0, and we immediately read off what the constant term was. So here I just went ahead and put that in. So we know the constant term. Now I want to find out what should be here. Okay, so we need once again a little bit of linear algebra from Rob 101. Yeah. So it was a derivative, right, when we did it for scalars, so a little bit of linear algebra from Rob 101. We have a matrix, and we write it in terms of its columns. So A is m by n, so this is going to be m by n as well. So m rows, n columns, these are the columns. Each of the columns is just a vector in Rm. It has m rows in it. Okay? Now, do you remember what would happen if you multiplied a matrix like that times one of these natural basis vectors? I'm guessing you need a refresher. So if we have A1, A2, dot, 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 AN, this may be easier for you. X1, X2, Xn. So do you remember the second way of doing matrix multiplication? You used it for doing the LU factorization. Where we're used to doing, so it's looking at you, you're used to doing the finger tracing method where you take the row times the column, right? The other way to do it is you take the columns times the rows and you add those up. And that's what we use for the LU factorization. You can get it with the finger tracing method as well. Okay. But it's easier if you remember that you can multiply columns of A times the rows of B and add those up, and that's what we've done, the sum. So if you accept this, what happens when you replace X by 0, 0, 0, 1 in the ith spot, 0, 0, 0? Zero, 0, 1, multiplying AI, 0, 0, 0. You see what you get? You just pull, it just picks out the ith column of the matrix. So it's just something to remember. A times EI equals AI. Okay, so we're going to use that to figure out what this matrix is column by column, and we'll stack them all together, and we're going to arrive at something that's called the Jacobian. Okay, so I've got my approximation. I want to make a perturbation about x0. So I'm going to take x equals x0 plus h times EI. So I'm only going to perturb one component. So then I end up with f of x0 plus h EI equals f of x0 plus A, and then this would be x0 plus h EI minus x0, and those guys cancel. So I get A times my small number h times the ith natural basis vector. Okay, why did I choose this for x? I'm just perturbing things one element at a time. That's the key to understanding partial derivatives. But now, take x0 plus HEI, I subtract off f of x0, and I've got this h here, and I divide by it. And these are approximately, okay, so this is approximately A times EI, and it's important to us that that's the ith column of what A is supposed to be. And in the limit, when h gets really small, okay, so just my approximation should be more exact as my perturbation goes to 0, so my x values get closer and closer to h0, and that's simply the partial derivative of f with respect to xi evaluated at the point x0. Ith column, ith variable. Okay, that's how we just figured it out, column by column. And so this matrix A is really df dx1 of x0. df, you just stack them up as columns of the matrix. Because f has m rows and there's n variables, n by n. And this thing has a name, it's called the Jacobian of f. And here we've evaluated it at the point x0. So it's this matrix of partial derivatives, okay? So back in the day when you had to do all these things by hand, this was not fun news that you had to work with Jacobians, okay? It was not fun news, because sitting down calculating them, the matrix is 3 by 5s, you've got 15 Jacobians to compute, 15 derivatives, and you're going to mess one of them up for sure, okay? There's almost no way you're not going to mess up at least one of them. So, but now I'll show you just a little bit. We have nice tools for doing it. And so, definition. J sub f, and I'll leave it as a general function, by definition equal to, and you stack up, and you leave x as a variable. That's the Jacobian function. And it's sometimes also denoted partial f of x without the I. Okay, so here we're denoting the ith column. The first column is x1, the second column is x2, the nth column is xn, and this is all of the x's. It's the same thing. Okay, so this is just a nicer version of the, come on, I'm not searching for anything. Thank you. Of the calculations we went through. Okay, and then the definition of the linearization at or about the point x0, here's our linear function. It's f. It's just a vector, constant. And we have this intimidating matrix that we have to compute. And then it multiplies the deviation in x about x0. N by 1, n by n. So all the sizes work. So in these large language models, you're seeing they have, there's one just came out recently, and the last 3 parts of its name is 32B. That stands for 32 billion parameters in the large language model. And they are computing partial derivatives with respect to each one of those parameters, okay? I bet they're not doing it by hand. What do you think? Okay? So, these things can be computed and at scale. Okay. Chapter 5. Okay, so the previous part of those demos was how we did derivatives for scalar valued functions. And the first part of this is going through and doing in code the same thing that we've just done with paper and pen. So there's the natural basis vectors, written a little bit more nicely than I do. Here's our vector x. When we say a function of, we typically write x as a tuple. You almost never write f on a paper with the x1s and x2s and things up and down, though in code, we're treating f as a function of a vector, so you certainly could write f of vector x1, x2, xn, okay? This is just the exact definitions that we had. We perturb one component at a time, about a fixed value, and then we let that fixed value vary and we get a function. And this should be n and m. I'll fix that. Wow, the things you notice when you're here live and you don't notice otherwise. Okay, so here's the case when the function has 2 components and it takes values in the reals. It's nothing too outlandish, but we could still make a few mistakes. Partial derivative respect to x1, we've got exponential of x1, treat x2 as a constant. Got to do cosine minus sine of the 2x1, etc. So we can do it. What I want to first emphasize, though, is once we fix x0, and then we create the functions by just adding h times one of the natural basis vectors, that g1 and g2 are just functions of h. Okay, so okay, what happened to all my answers? Okay, looks like we have to run this again. Run all. It's quick. If the kernel is connected. I don't think you're running anything. Kernel interrupt successful. Restart. Kernel has been restarted. Run all. Okay, now we're running. Okay, so we'll get these functions h, we'll plot them to see what they're doing, we'll look at the standard derivatives for slopes, and then we'll compare that to the partial derivatives, just to, once again, help convince ourselves that partial derivatives are simply ordinary derivatives done one variable at a time. Okay, so where are we here? We're still running. Yeah, getting closer. Okay, so there's the function. Got a number, it's 3 and pi over 4, the natural basis vectors. Are those visible enough? 1, 0, 0, 1? Okay, so here all we've done is substitute in, yeah, go ahead and run. Otherwise you're just going to keep scrolling up on me. Go ahead, do it, do it. Okay, got to the end of the road. Okay, so we take the function f, we define functions g1 and g2 by simply replacing x by x0 plus h in the first component and x0 plus h on the second component. So here we're doing it not with the natural basis vectors. That will come back to us. Okay. So here's g1 of h, there's g2 of h. We can only plot one component of f at a time, right? So here are the first and first components of g1 and g2. And then there's the derivatives as function. This down here is h. And we're doing the derivative at h equals 0, which is the partial derivatives at x0, which was 3 and pi over 4. Okay, so that is the partial derivative with respect to x1 of the first component, and that's the partial derivative with respect to x1 of the second component. And we could redo that for the other components. Now, you don't really want to compute them that way. You want to use the native functions in Julia. So here's a nice function. And to get the Jacobian, you just say symbolics dot Jacobian. Now the only thing I'm pointing out here, our function is scalar valued, and the Jacobian function in the symbolics package wants f to be a vector. So by enclosing it in brackets, we make it a 1 by 1 matrix or a 1 by 1 vector, however you want to view that. In Julia, those are not scalars, okay? So if you just put f without the brackets, it's going to complain that the type is not correct. The Jacobian function is typed where this should be a vector, column vector, and this is the column vector of variables that the function depends upon. And then it just goes ahead and calculates the Jacobian for you. And because the function just has one row, we put df dx1 in the first column, df dx2 in the second column. This is a 1 by 2 matrix. So there's df by dx1 is the first part, and df by dx2 is the second part. This doesn't really show up much. A little bit, I guess. Now here's the vector value case with the indices the way I had them in lecture. And here is the first column, all the derivatives with respect to x1. Come on, why'd you do that? Okay, so F has m rows, the Jacobian has m rows, and the first column is all the partial derivatives with respect to x1. The second column is all the partial derivatives with respect to x2, and the last column is all the partial derivatives with respect to the last variable, which here is xn. That's the Jacobian, or the Jacobian matrix. And symbolics just eats it up. Okay, you just give it the function. Here's the function. It's simple. It only has 2 rows. We only have 2 variables, so the Jacobian is going to be 4 by 4. And bingo, it'll just compute the Jacobian. It'll simplify it for you, etc. Okay, so you don't have to do all these things by hand. And then the linearization, exactly as we had it. And then here, trying to give you a little bit more of a physical interpretation. So I'm going to give a function, and suppose that z equals f of x1 and x2 maps out a portion of a sphere. So as I vary x1, I get a part of a circle. I vary x2, I get another part of a circle, and I'm building a sphere as I vary the 2 of them. Okay, so that's a 2-dimensional surface. When I compute the Jacobian, I'm getting a linear approximation of the function. So what should a linear approximation of the sphere look like? Sphere is 2-dimensional, and I'm doing a linear approximation. What should that be? What geometric object that you've seen in high school? And you probably drew it like once in Rob 101. Okay, so if I take one variable, I would get a line. But if I can vary 2, I fill up a plane, okay? So the linear approximation of something curved should be a plane that's tangent to a point on the surface. So just like the rise over run is a tangent line on the curve, this is a tangent plane. So there's a patch of a sphere. And there's what you get with the Jacobian when you build the linear approximation. So what you are doing is, instead of moving x1 and x2 and you're getting all the details from the curvature, you're now moving in a much simpler space, a plane. And if you're trying to find a solution to a set of equations, it's hard when there's sines, cosines, square roots, etc., right? So this has square root of r squared minus x1 squared minus x2 squared. It's not that complicated, but still, to move along the surface, what you can do is have an algorithm And that's what Newton-Raphson and gradient descent, all these powerful algorithms, they move on the surface and then they project themselves back down. They move on the plane, then they project themselves back down to the surface. It's easy to find directions here to move and solve linear equations, and then you interpret them back on the original function. So that's what the Jacobian does. Replaces the challenging nonlinear and curvy coordinates you get in your nonlinear function with a linear representation. And then this is just, this package I like a lot. If you just want the Jacobian at a point, you don't need to get all of the symbolic representation and then do all of the evaluation. You can just build a function, nothing symbolic here, just a normal Julia function, and you say for a diff dot Jacobian, and then you put in the function and the point, and it gives you the Jacobian matrix. So this Jacobian matrix is 2 by 3, and it's because f depends upon 3 variables, x1, x2, x3, and it has 2 rows. So the Jacobian is 2 by 3. So there's 6 derivatives being computed. df1 by dx1, df1 by dx2, df1 by dx3, and df2 by dx1, df2 by dx2, and df2 by dx3. It just does it all instantaneously. And I think I'll skip this because it's time for a break. And when we come back, we'll have a slightly new topic to work on. So take a break, get a snack from Max, ask questions. There's one more structure associated with these partial derivatives. It's called the gradient, as in gradient descent, that you've heard about maybe several times. We'll do it Wednesday probably. Right. When we're doing gradient descent, we'll introduce it then. Since we've done partial derivatives, what is a total derivative of a function of several variables? Okay, we got partial derivatives and we got total derivatives. Okay, so here's the setting. You've got this function, it can have multiple components, so first row, a second row, a third row, etc. And it's depending upon several variables, and once again, I'm kind of writing it the old-fashioned way, right, as an n-tuple and things, but I think it helps for understanding. So the setting is we have this function of several variables. And each variable is really a function. Okay, so in reality, we have this function g of t, which is just f, and you go and you plug in all of these functions. Well, often plugging things in is just painful. But yet you still want to compute the derivative of g with respect to t. So you want to compute g prime of t. And I'm going to write it in the Leibniz notation. That looks like a Q. It's supposed to be a G. And you want to do it without substituting everything in. Okay, so the situation is really like the chain rule. When we had f of g of x, we would first differentiate f with respect to its variable. Yes, g gets plugged in, and then multiply by the derivative of g. That's the chain rule. Well, the total derivative is exactly the same thing. It's just the chain rule on steroids. So it's simply you take first the derivative of f with respect to x1. And it has all of its variables in it, just like with the chain rule. And then you multiply by dx1 by dt. And you do that for the second variable. So it's just the chain rule, the second variable. Just the chain rule on steroids. And then you do it with respect to the last variable. And surprise, surprise, you differentiate that last variable with respect to time. So that's the total derivative. We take all the partial derivatives with respect to each variable multiplied by the rate of change of its variable, x1, x2, xn. That's what the dx1, dx2, dxn are. And you add them all up. Now, linear algebra makes this a lot cleaner because it's really the Jacobian of f evaluated at x of t times the vector dx by dt. Whoops. I've got to differentiate these things. Respect to t dot 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 dxn. So once again, all the dimensions work out, n by 1, m by n, and so the product is m by 1. So if f has m components, when I plug in sine of t, cosine of t, e to the t, hyperbolic cotangent of, I don't know, this room's length into the variables of the function, g has the same number of rows. G has the same number of rows as f. And you can turn this into a simple vector calculation by the total derivative is the Jacobian of f with respect to x, and then you just, it's a function, you throw x of t into it, and then you multiply by dx by dt. So it's just the chain rule on steroids, and it gives, if you use vector notation, this is what it means. It's the sensitivity of f with respect to x1 times the sensitivity of x1 with respect to t, plus sensitivity of f with respect to x2 times the sensitivity of x2 with respect to t, plus all the way to the end. But you can do that in Julia and all the other modern programming languages by a simple matrix vector operation. Calculate a Jacobian, evaluate it at a point, and then multiply it by the derivative of x, and that's the total derivative in vector form. Matrix vector form, I guess. So when I was a student, there's no way we're calculating this matrix and then this other vector and multiplying them out. We do it just by the definition. We just write out each one of those things, but God, it's so painful. But now in Julia, you just calculate a Jacobian, it's a function, you evaluate it at whatever point you got in times dx and you're done. So total derivatives are totally easy now. Okay, so it just takes all the partial derivatives times the rate of change of the functions that depend on. So, okay, so that's the end of chapter 5. Because we delay gradients until Wednesday. So we're going to start chapter 6, which is applications of the derivative. And it's going to be mostly applications of vector derivatives, meaning partial derivatives, Jacobians, eventually gradients and things. But we're going to start off with something a little bit simpler. So we're going to start with arc length and path length. It's also called path length. Highly visual. Grizzle's fantastic plots. Okay, here's 2 points. If I connect them by a straight line, can you tell me the distance between those 2 points? Okay. So distance from A to B, it's the Pythagorean theorem. So it's going to be XA minus XB squared plus YA minus YB squared square root. Right? So I'm not going to draw those, but you could put a dotted line here. That's the XA minus XB, and then the YA minus YB, and this is the Pythagorean theorem. That's the length, no doubt. Okay? So if your robot is going from point A to point B, and there's no obstacles, so it can go in a straight line, you know the length of its path. Okay. What's the length of that path? Okay. And instead of compute, I could almost put the word define. Okay, so how do you even define the length? Okay, we know the length of straight lines. Okay, so you can see where this might be useful if you're trying to do robots and planning and they have to fly around buildings in a window, and you're trying to find a path of minimum length that avoids obstacles and uses the least amount of battery charge or fuel or whatever. Okay, so path length is something that's interesting. Okay, well, we know calculus. Let me just get part of a curve here. We'll just, this was some small length, delta xi. And this is some small length, delta yi. And then I connect those as a triangle, and I call that delta si. Okay. So what am I suggesting that we do? We do what we always do in calculus. We break things down into small little pieces, and then we use integration to add them all up. Okay, so I know the distance. If I can approximate distance well with a straight line if I make delta x and delta y sufficiently small. So this is y equals f of x. Okay, and I've done a zoom into a little area. The letter S is Latin. I guess it should be capitalized. So that's why mathematicians use it. Math used to be written in Latin. It's Latin for, it can be interpreted as space or distance. And I'm taking this from a higher authority, Wikipedia, because I've never studied Latin, okay? So I don't know about you guys, so hopefully you went to a really great school and you learned Latin. But no, okay, so we're gonna use S for arc length. And so this delta SI is just from the Pythagorean theorem. It's delta xi squared plus delta yi squared. And then the total length will be the sum I equals 1 to n of the delta SI. And then we'll take the limit as n goes to infinity to arrive at a Riemann integral. So the process looks a little bit different. We're not drawing a rectangle and adding up the area of the rectangle, but we're still breaking up the curve into these little pieces, delta xi. We've got an xi and xi plus 1. We calculate the distance there, and we add up all the distances, and that's the whole, doing these infinite sums. As the number goes to infinity, that's fundamentally the Riemann integral. Okay, this makes sense to you? So we're gonna derive it, and then I'm gonna show you some examples where we take a curve like this and we put 5 segments in it and we're within 1%, okay? That's how good this answer is, okay? It converges really quickly. So, calculus works. So here's case 1. There's 2 cases that are interesting. Case 1 is like the one I drew, where y is a function of x. So then delta y is f of x plus delta x minus f of x. So delta x is the run, delta y is the rise, okay? And so what I'm going to do now is multiply and divide by the same quantity. Okay, I haven't cheated. Delta y is still the rise, but I'm writing it in a way that now we take the limit as delta x goes to 0. Now, x is a scalar here in my picture, and that's how it is. We're doing paths in R2. You can also do paths in R3, but we're doing it in R2. Okay, so this converges to the derivative. And then as delta x goes to 0, that gives us the dx that we use in under the integral sign. Make sense so far? Just here's the run, here's the rise. Okay, I multiply and I divide by the run. So I can recognize this as being a derivative, and then this is just an infinitesimal increment. So this is similar to what we were doing for area and things, very similar. Okay. So what is delta S? Remember, that was delta x squared plus delta y squared. Delta x goes to 0. Well, that becomes dx squared. And delta y, that's f prime of x dx squared. And I wish my sheet of paper was longer, but it's not. So what I'm going to do now is factor out the dx, keep it as positive because length is positive. Then I'd have 1 plus f prime of x squared. And that's my infinitesimal length. Okay. So what I've done is taken this picture, delta x, delta y, for the special case where y is a function of x, calculated all the increments using our knowledge of derivatives, and have a convenient formula for an infinitesimal length of my curve, and then the total length will be the integral from a to b of ds. That's how calculus works. I guess that should be a larger S. So it's the integral from a to b, square root of 1 plus f prime of x squared dx, because we like our dx's to be at the end, though there's no rule that says you can't keep the dx in front, okay? It's just conventional to put the dx at the end. So that's the formula for the length of a curve when the curve can be written as y equals f of x. So it has to pass the vertical line test. Okay, let's see. So when you study this in a standard math course, about the only thing you can compute it for is the length on a circle, which is radius times the angle, okay? So it's something really boring. And if you've got a much more interesting curve, you can't do it. But you guys would use quad GK, okay? To the rescue, and it's a, okay? Case 2 is super cool. I'm not going to draw this very well, but I'm going to try. Does that curve ring a bell to anyone? Do you wonder how I computed the path length for you guys? You didn't, because you were just trying to
You were just focused on, I don't want any more of those crash symbols showing up, okay? And you remember how complicated the blue thing when it was dodging? I mean, it was just a mess, right? So, yeah. X, Y. So this curve is parameterized by some independent variable. Clearly, y is not a function of x. It fails the vertical line test, okay? It's not a function. So how do you calculate the length on this? Well, Grizzle, you made it flat right in the spot where you wanted to put a curve. So I'm going to redraw it where I've got a nice curve here. Please, be nice. There we go. Best figure eight I've ever drawn in my entire career. Okay, so it's the same thing as before. We do a delta x, we do a delta y, and we have a delta s. We need to add them all up. And we're going to use the Pythagorean theorem in the end. So delta x here is going to be t is incremented, the parameter. It doesn't have to be time, though in our example for project 1, it was time, okay? So it's time with these crazy things. So the increment is x minus x of t. Take the limit as delta t goes to 0. And you end up with, I'm going to write it as dx, the derivative in the Leibniz form, times dt. And I'm writing it like this for the same reason that the mathologer liked it, because I'm going to cancel those here in just a little bit, okay? Remember the mathologer taking the, he did it for the product rule and the chain rule and rearranged everything and showed how these increments could be canceled, okay? And the delta y, it's the same. I'm cutting it a little bit shorter than we did the other one, but it's the same idea. I multiply and I divide by delta t, then I take limits as t goes to, delta t goes to 0, and I'm going to get y prime, if you wish, but when I write it as y prime, I can't cancel my delta t, so I like this notation better. And then ds is the Pythagorean theorem. dx by dt of t, dt squared plus and I've got a dt squared and a dt squared. So I'm going to take that dt out. And now, whoops, that's kind of ugly. Let me write it. dx by dt squared, and I'll take the square root. And then I do the same as before, except now, whatever the initial values of my parameter are. I don't have points A and B, but my curve is parameterized by, say, time, and it has an initial point and a final point, and I just add up all the DS's, and so this becomes T0, TF, and it's probably prettier to just write it in the prime notation at the end, dt. So now we'll do a demo. Okay, so we can calculate distance along a curved path just using the Pythagorean theorem. And we just add up all of these small little distances. We do that one, we do another one, we do another one, and calculus is making those things infinitesimally small. So let's see what this looks like. Okay, arc length, ACA path length. We're going to use quad GK. For the first function, it's going to be y equals x squared. We know the derivative, though we could compute it using tools in Julia, but it seems kind of overkill. We just write it down. And so the integrand for the arc length is square root of 1 plus the derivative squared, okay? We're going to go from x equals 0 to x equals 1, and we'll use quad GK to calculate the integral and get the error. And then we're going to use only 3 points. So here's the curve, and the true arc length is 1.4789, 1.4789, and the error is 1 times 10 to the minus 8. Got it? Now we do our back of the envelope calculation, okay? So we just connect it with 3 points, evenly spaced. And we take this distance plus this distance, and we add those up, and it's 1.47. Okay? 1.48 when you round it, and here's 1.47. So you see how it's stupid how cool of an approximation you can get. In the book, I do it for the figure 8. Take a look at the figure. It's kind of fun. Here's a much more complicated curve. And I think what I do, 10 or 12, 1, 2, 3, 4, 5, 6, 7, it's like 10 segments, okay? You just add them up by just doing the Pythagorean theorem on those segments and add them up, you get 1.57. And then the real answer is 1.59. Okay. So when you have data and you don't have a function, guess how you are computing arc length like I was doing in project 1. I knew the position of the drone here, delta t path where the position of the drone here was. I knew delta t. I could calculate the rise over run and just add those up. Okay, that's all I was doing. So, yeah. And then you could do stupid things like, this crazy function, what is the arc length? Like someone cares. But the arc length of that function from 0 to 3 is 5,171.7. And then there's the figure 8. So you can go into Julia its real length is 1.58, and you can estimate 1.4 or something with just like 8 segments on here. So going from here to here to here to here, and then doing 4 more over there. So that's it. So that's arc length and path length. And unless you guys want to do more, I'm happy to call it a day right here. You want your next 13 minutes? I'll just be up here answering questions and stuff like that. Is that okay? Good enough? Yeah, we were efficient doing the Jacobian Tate, so that's good. Okay. And we've got tools, and then we're going to start using those Wednesday. And Wednesday we start getting into gradient descent, and hopefully we'll also get into gradient descent with equality constraints. So that's really cool, very important for applications.